Let us start. Okay, good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm the interim director of NITheCS. And if you're not already on our NITheCS mailing list, please join it ASAP. So this afternoon, we are very fortunate to have Professor Hargrove with us, who will speak about a very interesting topic, tsetse flies and climate change. And Professor Hargrove did his honors degree at Oxford in zoology, and did his PhD later at Imperial College, where he already started getting interested in the physiology of tsetse flies. Yeah? And over many years, he will tell us now about his experiences. He also worked on other topics, but that probably for a talk on another occasion. Yeah? So Professor Hargrove, you're most welcome to start with your talk. Thank you very much for being with us today.
Thank you, Francesco, and thank you to NITheCS for inviting me to come and talk about the work that I've done with many others, but particularly with Glenn Vale and Steve Torr in Zimbabwe on tsetse flies. Okay. Get used to this. All right. So tsetse flies, genus Glossina, infest about 11 million square kilometers of Africa in 37 different countries, and they cause particularly damage in the agricultural sector to the value of several billion a year, according to FAO. But I want to talk today about climate change, and particularly about work done on these matters in Zimbabwe over the last 50 or 60 years. Now, while I'm doing that, I want to answer various questions. First is, have there actually been have changes in climate in Zimbabwe actually affected tsetse flies there? And secondly, what effect, if any, will further changes have? Also, of course, does the Zimbabwe work on tsetse flies have actually any relevance for tsetse flies outside of Zimbabwe, or is it just merely local interest? And finally, can tsetse work provide lessons for other vectors, particularly insect vectors of disease? Now, an awful lot of work has been done on climate change and on vector-borne diseases, particularly things like malaria. And it's been carried out basically by considering the relationship between observed climate and observed disease distribution without reference to the observed changes in vector populations in the field. Much less money is spent on field studies of vectors than is spent on the diseases themselves. And so there's much less information about field population dynamics. But there's an exception to this rule in Zimbabwe, where research on Tsetse has been carried out at Rekomitjie Research Station for the last 50 or 60 years. And I'm going to be talking mainly about that work. Now, here's Zimbabwe, which just is, of course, our northern neighbor to South Africa. And it's bordered on its north by the Zambezi for a lot of the time. Zambezi coming into Victoria Falls into Zimbabwe. There's the huge Lake Kariba, and then flowing along the Zambezi Valley. And you see there the Rekomitjie Research Station is shown, if I can get the, so in the Zambezi Valley. So that's what I'm going to be talking about. Now, it's in the tropics. It's 16 degrees south, and it's only at 500 meters. So it's low-lying. It's in the tropics, so it gets extremely hot. It can get over 40 degrees centigrade quite regularly in the summer. But from the tsetse flies point of view, it's in a national park, in the Monopools National Park, which is a huge park covering a vast area of the Zambezi Valley. There's lots of good large animals there: elephant, buffalo, kudu, warthog, and so on. So it's prime tsetse habitat. And it also provides a unique opportunity to study changes in fly populations in an undisturbed natural situation. So here is Rekomitjie, and what you can see here are some buildings, the offices here, and we had large numbers of people who were living down, who were the workers and on and on. But there's little conurbation here, but there's nobody living anywhere 30 or 40 kilometers going in any direction. So it's a wonderfully undisturbed piece of country in which to work. Down at the bottom, you see a dry sand, which is the Rekomitjie River. And if we step back a bit, and you actually see on here, you can perhaps just see it, traces cut through the bush. These were put in 40 years ago by Glenvale and then by me. And it's there that we've done the vast majority of the work and the studies I'll be referring to later on. And there's the Rekomitjie River. Now, when the rains come, you get an explosion of vegetation, massive explosion of vegetation, and you get loads of buffalo and elephant walking in, as you can see here, and they really have a great time. And if you get a sufficiently good rainy season, you get a vast flood on this river. It looks more frightening than it is. It's only about 3 feet deep, but it can get to be 100 meters wide. But for the most of the year, it doesn't look like that. Most of the year, it looks like this. It's very, very dry. The only water now is actually under the sand, and the only way that animals can get it is basically through the elephants, which dig in the sand, and then others can access the water. But we're not here actually to talk about the elephants. What we're talking about, we're going to be talking about the tsetse flies. And for people who don't know about the tsetse flies per se, I'm just going to do a quick whiz through their biology and their life history. So this is a pregnant female, and it's just absolutely amazing to see this, what happens when this tsetse fly gives birth, because it extrudes a larva which actually can weigh more than the mother itself. So you'll not be surprised that this doesn't produce too many, not very, very frequently, but it only produces one at a time. But the plus side is that unlike mosquitoes, which lay eggs, which then have to go and find their own food, this doesn't have to find new food. It's got everything inside it that it needs to form the adult tsetse fly. So what does it do? It burrows under the substrate where it's been placed into the sand or soil, and then it forms a hard melanin case around itself, first orange and then completely black. And inside that pupareal case, all of the metamorphic changes occur, which are required to produce an adult fly. And that's an adult fly, and which will actually then pop out and harden in the way that you've seen, I'm sure, butterflies expanding. And then the fly has got to go off and actually find its food. Now, both the males and the females live entirely on blood. And therein lies the problem from the human point of view and the farmer's point of view. So they take a huge amount of blood. And while they're doing that, the fly, which is born uninfected, if it bites an infected animal, it can pick up trypanosomes in the blood and pass those trypanosomes on. So that's where the whole problem comes along. Now then, these are cold-blooded animals. As you would expect, almost all of the vital parameters are strongly affected by temperature. And so, for example, if we look here, you saw that the fly burrows under the ground and forms a pupareal case. And then we see what happens is that it takes the length of time that it's under the ground is this sort of exponential function of temperature. If it gets up to 30-odd degrees centigrade, then they'll come out in around about 20 days. On the other hand, if it goes down to 17 or so, it gets up towards 100. Now, what's happening, of course, is that as it gets hotter, the flies are using fat more and more rapidly. So if it gets too hot, they use all the fat, and then they die before they come out. If it's too cold, they use fat very slowly. But on the other hand, it takes such a long time that they also die. So at both ends of the spectrum, they can die simply of starvation because of the imbalance between the rate of use of fat and the rate of development. But up at the top end, it's actually more serious than that. Flies the pupa can actually survive quite nicely at 4 degrees centigrade even, but once it gets above 32, they simply die. 32 is a bit of a magic number, and we'll come across this as we go. 32 degrees centigrade, things start getting rather nasty for the fly. Now, what we'd like to do is we want to actually measure in the field the various rates which are going to control R0, the rate at which this fly's population is going to increase. So we need to know basically the birth rates, that's the inputs, and we need to know the death rates, that's the sort of the losses. And we can do this all using mark release recapture, MRR, to estimate things like that. And what we do there, so this is a fly held between thumb and forefinger. They're pretty robust flies. You can treat them quite roughly and they don't seem to mind terribly much. But you we're using a matchstick or so, you put a little dot of paint on the fly on a position which indicates where it was released and when it was released. Then you let it go and you then recapture flies. And if you're lucky, you catch some back. And you from the mark of when you released it and when you caught it, you know how long it's been out in the field. And then the next thing you do, and this is basically just for the females, is you do an ovarian dissection. Do essentially a hysterectomy, a radical hysterectomy on this fly. You pull out the uterus and the ovaries. And when you look at here we've got the ovaries sitting up here, and there are two ovaries, paired ovaries, and two ovarioles in each ovary. So we've got 4 to go. And basically what happens is that these ovulate in strict order. So it starts on this right inner here. When that's ovulated, then the left inner. And so basically by looking at the relative sizes of and positions of these the oocytes in the ovaries, you can tell how many times the fly is ovulated. So if you know how many times it's ovulated, and you know how old it is, you've got the chronological age from your mark recapture, you can then figure out the rate at which it's producing offspring. And you will not be surprised to hear that, again, this is a strong function of temperature, okay? So when it gets up to around about 29, 30, they're producing an offspring every 7 days. On the other hand, if it's around about 20, it's taking them 17 or even up to 20 days to produce an offspring, okay? So that's a function of temperature. Now, when we want to measure the mortality, this is rather more difficult. And again, they go back to mark recapture. So when we're looking at birth rates, we could just actually get flies which emerge from a pupa, let those go, and that's fine. When we're looking at mortality, what we do is we will go out and just have an ox in the field, and the people will catch the flies off the ox and again put the mark on it and release it in the same sort of way, and then you try and catch the flies back. Now, there's a problem here, because what you're looking at is the rate at which these marked flies are lost, which will give you an idea of the mortality. The trouble is there are two reasons that you might fail to catch a fly. First is that it's died. The second is that it may have gone to live somewhere else, and it might be perfectly happy. So it's hard to differentiate mortality and migration. You can get around that, however, basically by doing things on an island where they can't get off, and we can check that they don't get off these. They don't like to fly too far over water. And so Glenvale in the late 70s set up this experiment on Antelope Island, this large island, which is just out sort of 5 k's or so from Kariba town on this huge man-made lake in the north of Zimbabwe. And basically Glenn stocked this island with cattle, and so the flies had lots of food and they did extremely well. And you could do mark recapture exercise, mark them each week with 1 mark. If you caught them again, put another mark on. And this gave you a very, very good idea of what was going on with the population of the flies. And what went on with the population of the flies, basically what you can see is, one more time, is that there is a very strong relationship between the average daily temperature and the mortality as measured by mark release recapture. Mortality higher in us crummy old males, just like the human populations. The males pop off first. But for both of them, the hotter it is, the less they like it. And once you get up to sort of 32, you're getting to be at quite large mortalities. What we can also do, one of the nice things, and we're going to come back to this slide later on in my talk, is that you can estimate the absolute number of flies. Using the mark recapture, it tells you how many flies you've actually got on the island, and therefore the population density, because we know it's 5 square kilometers. But then what you can do is actually look at the number of flies you catch. So you send an ox out each morning and afternoon, and the ox was sent out, stayed out for 2 hours, and you looked at the number that you caught on the fly run during that time, and you plotted that, against the estimated population. And you see, again, we've got this very, very nice linear relationship. I think that's probably on a log scale. Yeah, these are on, so the log there, it's a power function there. And it's the same for the two species that we're working with, Glossina morsitans and Glossina pallidipes. So this is all hunky-dory on an island. But of course, we're not interested in the island. We would like to know what's going on at Rekomitjie in a real, this is an artificial, Lynn actually introduced the flies onto the island. But at Rekomitjie, they're there all around. And what are we going to do about Rekomitjie? The trouble is there, as I said, using mark-release recapture is a pain in the butt because you can't separate between mortality and migration effects. So another possible way of doing it is to actually do what demographers would do. You know, people who work on human populations, is you essentially look at the age structure of the population, and from that you can work out mortality rates at each age. Well, we've got to do this slightly differently with tsetse flies, of course, because we don't have birth certificates and one thing or another. So again, what we have to do is catch the flies, do the ovarian dissection, and find out how old they are. But of course, first you've got to catch your fly. And how are you going to do that? Well, work in Zimbabwe, really pioneered by Glyn Vale, led eventually to the identification of 5 different chemicals which are important odor attractants for tsetse flies, and also to the development of nice traps. And so it's quite simple to put traps up with odor, and you can catch flies, and there you go. But there are other ways of doing it, and what we're going to find out is that the results you get can depend rather heavily on the way in which you catch them, which is makes things difficult but also interesting. So, for instance, instead of having a stationary trap, you can have a Land Rover here with an electric net on the back, and the flies, it drives through the bush, and instead of the flies having to come to you, you are going to the flies and you catch them there. And alternatively, also when it gets really hot, Glyn also developed this method where you have a drum covered with soil, painted black on the inside, and with a nice big thatched frame in front of it. When it gets really hot, the flies don't like it, so they head off to dark places, and dark places are cool places. And so you can catch large numbers of flies there. And similarly, in the hot season, it's too hot for the pupae, so what they do is they go down warthog burrows, which are much cooler. And so what I did was actually to invent these artificial warthog burrows made out of cut and welded 44-gallon drums, and you catch flies there. And the interesting thing about that is it's the only time you can catch a female fly while it's actually producing an offspring. Okay, so, but for most of the work, and the important thing about why I've actually told you about these various capture systems is that we've used a whole slew of a dozen or more different capture systems at Rekomitjie, and we would like to use the information from all of these things. But for the time being, I'm going to focus just on what happened with the flies caught in traps. Now, bear in mind, what I wanted to do, my basic idea for doing this thing was to say, what is the age structure of this population, and therefore, what is the mortality? And we will come to that later on. But of course, what you're doing is just you're running a trap every afternoon for just a couple of hours, and you see how many flies, and you capture all these flies, and then you dissect them. My team dissects them. And so we've got an idea about how many flies we're catching. And what you see in general is that the numbers go up and down as a function of month. When it gets in the hot season, they tend to go down, but then they go up when the rains have come, and then they go back down. And it goes along quite happily from the end of 1988 when I started until November 1992. And then suddenly the wheels fell off. Now, this is a log scale. So this is 250 flies caught here. And then in that month, it dropped to 10. Went down by a factor of 20 in 1 month. This was just incredible. We'd never seen anything like this before in the 50 years that we'd been working at Rekomitjie. And then, of course, what happened was that, well, it recovered somewhat with the rains and went up a little bit and was not too bad. 93 was a reasonable year, and but then 94, 95, 96, population went down and down and down. So this is interesting. And if we actually then, what I need to tell you is that the whole time we've been at Rekomitjie since October of 1959, every day, minus a few during the Independence War, we've recorded the maximum and minimum temperature and the rainfall. Okay, So we know what's happened with the temperature over these periods. And what you can see is in these times when we saw suddenly the population taking a big nosedive there and there and there and there, what we had were extremely hot years. So it looks like basically what we're seeing is that what we're getting is that high temperatures are leading to these big declines in population. Now, trouble was in 1999, we'd actually been so successful at Rekomitjie that all the funders said, look, we not want to support you anymore. You've discovered how to get rid of these tsetse flies. Why don't you go and work on something else? And so they stopped all the funding. And I was out on the street, and I still had 2 kids to put through university. So I went off and worked on HIV for 10 years, as Francesco indicated. But I then, after that time, managed to get back and started looking at these fascinating data again. And after I'd gone, Glenn Vale, God bless him, had kept things going in another area. So because what I'd like to know is what happened after this? Did we continue to see this problem developing? Because this looks like it was reflecting some manner of climate change, even by 1999. And so we actually had a very nice system for checking this, which he didn't design the experiment this way. All he was doing, he was providing a service to chemical industries to test insecticide. So what you want to do is test them against a good, robust fly. So the Antelope is the biggest fly. Females are bigger than the others. And if a fed fly is more resistant to insecticide. So what you want is the most robust fly. So send a team out and get them to bring in every day 50 Glissan Antelope females, which are fed. And basically you said to the team, catch those flies and you can go home. And indeed catch 50. They actually loved this in the 70s and 80s. Because in fact, all that time, they were always catching 50 flies. This is again, it's a log scale, but all the way up to 1990, it was always fine. They could always catch 50 flies. But then things started getting a bit funny because every now and then they weren't catching so many. This is when the wheels fell off I show you with the traps. There's a sudden decline here. They could only catch 25 flies. And then things started going down. Then they sort of leveled off. They leveled off for quite a long time. And this has been kept going right the way through until the present day. And it kept going. And then suddenly in 2010, things started to get really nasty. And ultimately, the wheels fell off completely to the point where at the end of 2017, basically, I think we went from a situation where they were catching 50 flies per day up over here to where they were catching 1 fly every 10 days. So this is just a complete collapse of this population. And so let's see how this relates to what's going on with temperature. And again, we've got all these lovely data, and what you basically see is that whether you look at the maximum temperature, the minimum temperature, or the mean temperature, they've all gone up consistently and significantly. This is just a crude little linear regression, but so the maximum temperature has gone up by about 1 degree, the mean by 1.4, and the minimum by 1.8. And what you'll also see is that along there, once you get over here, suddenly, this is the 32 degrees centigrade. They're all these mean annual figures are actually all above that danger level of 32 degrees centigrade. We can also look not just at those, but actually now look at, because what we think is going to happen is sustained temperatures, high temperatures are going to really do the damage. And if you look at the 20-day running mean, and this is quite 20 days is not something that I've sucked out of my thumb. If you think about it, when it gets up to about 20 days is how long the flies are underground. But once it gets up to that sort of thing, you know you're going to have a lot of trouble. And before 1990, that only ever happened once, the entire time. But since then, it's actually gone up, 15 times. We've had a 20-day running mean above 32 degrees Celsius, and sometimes markedly more than 32. Okay. And at the bottom end of the scale too, only once since 1990 has the 20-day running mean gone below 19 degrees centigrade, whereas it went down below that level 8 times prior to that. Okay, so what we'd like to do is actually to do a model, find out, is it actually true that the temperature can really explain what has been going on here? I mean, it looks fairly obvious from that road, but let's actually try and construct a model. So Jennifer Lord at the Liverpool School of Tropical Medicine, where also, by the way, Steve Torr is based. I got the job to construct a simple ordinary differential equation model. I'm not going to send everybody to sleep by going through this, but basically just looked at the rate at which pupae are produced, the rate at which they produce immature females, and the rate at which the immature females become mature, and then the losses. And we basically we've looked at the things we've looked at: the rate of pupal development, which I've only showed you, the rate of adult mortality, at the pupal mortality. And then there's also a density-dependent factor, which we know we have to have in there. And so you think, well, this is a fairly simple sort of thing. And of course, we've got some good starting values because we've measured all these things in the field already. And hallelujah, when you actually use this really simple model, actually what you can do is come up with a very nice fit to the data, which is, this is all well and good. And we're very happy about that. And Jennifer Lord was very happy with the fit she's got. But notice that all we're doing is we're only fitting data from 1990 to 2017. Okay, so it's 20, there's actually 27 years. But there's this entire period over here where Jennifer says, this is what I think the flies, what the population should be over here. So it looks as if they're doing what we might expect, that they are actually just flopping up and down, but staying fairly sort of stable. But we've got nothing to check it against. Well, I say we've got nothing to check against. Actually, we've got quite a lot to check it against. Because whereas what Jennifer did was just to look at the population dynamics using just a tiny proportion of the available data based just on one sex or one species, sampled using one method over a limited period, we have got an awful lot more data than that available. This is a photograph of the director's office at SACEMA. And on this wall, this is not anything other than Tsetse data. All of this, these are the Tsetse data that I brought down from Zimbabwe. And a huge amount of this is not reflected at all. In fact, almost none of it is reflected in the modeling we've done so far. But it can be used to do that. So we've got data on the females and males of both sexes of Tsetse flies, and we've got it for the last 50 years. So now just go take a step back and remember what I told you about the stuff that was done on Antelope Island, because what this does is it allows us to get a nice relationship between the number of flies that you catch and the number of flies that are actually out there. And then, of course, if we do experiments where we actually use an ox fly round at Rekomitjie on the same afternoon that we use a trap, we can find out what the relative numbers are caught using different methods. So we can take all of our dozen different methods and say, right, we know how many they actually catch. Now this relates to this number of flies per unit area in the whole population. And so we can, with some luck, and of course I'm saying this very quickly, but there's a huge amount of work that's going to be involved in actually doing that. But the important thing is we have the data. We can, in principle, we can actually do this. So this is extremely interesting. Now, what I've said is that we can use an awful lot of different methods to actually produce data. What we can also do is we can get a much more nuanced view of what's going on than Jennifer got in her model. I mean, it was a very, very nice model, but we can do an awful lot better than that, because in what she was doing, for instance, she was looking, treating flies as if they were all equal in terms of their mortality. But we know that's actually not true from different market recapture experiments I'm not going to go into. But basically what you see is you get this very nice function relating mortality to age, particularly amongst females. We know that the males die much more quickly. And so what happens with them is that they really don't live terribly long at all. And so there is this aging effect. We need to include that sort of thing in our modeling so that we can get better fits to the data. Now, what I want to do now is to actually build up a picture of how various properties of the Tsetse population change through an average year at Rekomitjie. Because if you think about it, what's happening is you're getting changes in temperature, which is just like a miniature of what's happening with global climate change, right? You're going from really quite cold to quite hot, and what's happening during that time frame. So if we look here, what we've got is looking at the red graph first. basically, and by the way, this is a year starting in July and ending in June. The reason I've done that is so we've got the rainy season just not split in the middle. And what you see is as the temperatures go up towards October, November, what happens is the NDVI, that's the normalized difference vegetation index. It's basically a measure from satellite imagery of how much photosynthesis, in other words, how much plant growth you've actually got. So as it gets hotter and drier, as you expect, all the plants die off. And then when the rains arrive, boom, it goes absolutely berserk and up it goes. And what we see, if we look at the flies, is that if we look at the length of the wings over that whole 11-year period and get the average, we find that they just get smaller. As it gets hotter, they get smaller, and as the rains arrive, they get bigger. So, and we know this from various other studies throughout Africa, that basically small flies are an indication that the flies, that the population is under a lot of stress, and that therefore the mortality is going to be high when it gets very hot. So what we should expect is then, and we know from when we looked at the Antelope Island, is that as it got hotter, the mortality went up. So it ought to be true, you would think, that at this time of the year, when it's extremely hot and the flies are small, we should have high mortality. But the interesting thing is, when we actually look at this, if we look at the mean age of the flies we catch, it's actually highest at the time of the year when it's hottest, when we know the mortality has got to be highest. Now, think about the human population. Think about places like Japan and the Scandinavian countries, where people live forever. They've got a very high average age and a very low mortality. It's completely opposite from this. If you've got a third world country, where things perhaps are not going terribly well, what you expect is you will have a low mean age and a high mortality. So what's going on? Well, so let's just look at that. Well, those slides are a bit busy, but if we look at it here, what you can see is this is what we've got. So we've got it looks like the flies are getting smaller and therefore there's high mortality. But in fact, what we've got is the mean age actually going through the roof as it gets hotter. Well, we get a clue about what's going on. This is where the different sampling systems come in, and these different sampling biases which make life so difficult for us. And what you see here is if we actually catch the flies on a mobile device, then for most of the year, apart from the really hottest time of the year, actually, if you catch them on the mobile, the VET, it says, yeah, actually, they are actually really quite young. But at that same time of the year, the trap says, no, they're not. They're always old. It's only at this time of the year where actually both systems say that's extremely, they're actually all very old in average. And you can figure out what's actually going on. What is happening is that it is actually true that there's a massive increase in mortality when it gets hot. But basically what must be true is that what's happening is it's all the babies that are dying off, okay? Which is not really that much of a surprise, but it's really quite an interesting graph. And why should this be, particularly for tsetse flies? Well, the point is, when mummy produces that massive baby, she basically, she produces something which is bigger than she is. So she's got a big problem on her hands just to actually get that baby out. And she essentially says to the baby, look, chum, I'll give you plenty of fat, but I'm not giving you everything to make you another me. I'm giving you, you're going to be a bit short of fat, sorry about that, and you're going to be a bit short of flight muscle. So the thoracic weight is down compared with older flies, and the fat is way down. So these flies have got a bit of a problem. They can't fly very well, and they haven't got very much fuel to actually do the flying. So they don't feel like getting up there and doing a lot of flying until they can find an odor source and then find a trap. They'd rather sit there and wait for something to come by them. So that explains what's actually going on. So that was a very rapid walk through 60 years of work in the Zambezi Valley. And what do we want to do now? So what we would like to do is actually to develop a comprehensive model of changes in tsetse populations at Rekomitjie since 1959, using all the data, fly numbers, on fly ages, on fly sizes, nutritional status, and infectious status. And basing that model on the estimated effects of the met conditions on various population parameters. And what we then also like to do is to use the models to predict the future distributions of tsetse and trips in Zimbabwe and elsewhere. Nobody has ever been in a position even to attempt to construct such a model. For the good and sufficient reason is nobody's got the data like this. So this is a unique chance to be able to do that. And we have got all sorts of things. Just very briefly, so I showed you the trap catches, but here are the mean ages by month right the way across that 11-year period. And here's for each of them, we actually took the wings and we look at the degree to which they're afraid, which is a measure of age, and also a degree of a measure of how much stress they're under. So we can actually do that. And then finally, of the ones I'm going to show you, we've for a subset of the population, we actually dissected them and find out whether they were infected with trips or not. And you can see that again, this also shows a marked pattern with annual variation. Okay, so to go back to the beginning and to provide some beginning answers at any rate to the questions I asked at the beginning. Have changes in climate affected Tsetse? Well, I've shown you. I mean, it's perfectly clear. They're actually have huge effects of climate change on the Tsetse flies. It's actually really quite a good system to use to look at climate change. What effect, if any, will further changes have? Well, we've actually predicted it keeps going on, and like this, we get another degree change upwards in temperature. Tsetse flies will probably go extinct in the Zambezi Valley. But of course, up on the Highveld, they might very well do rather better. But that's another story. Does Zimbabwe work have relevance elsewhere? Well, it has, and basically we know that from the past. What basically happened was, as a consequence of Glenvale's, we're going to say interest, it's actually an obsession with getting the sampling systems right. It led to the development, led to him being able to show how important odor was for tsetse flies finding their host. That led to the work which actually isolated the actual chemicals which were involved, so we can make a synthetic cow, if you like. And that led then to using those odors with insecticide-treated targets to actually be able to eradicate flies, at least in the savanna areas. And then we basically were able to sort of say to people in Eastern and West and Central Africa, look, actually, your odors don't work so well for your flies, but look, if you actually just use much smaller targets, you can actually get good control. You can aid with the control of human trypanosomiasis in the East and West, and human the particular version of human trips in West Africa is actually on the verge of extinction. Basically, is being helped very much by the work which was done in Zimbabwe. Can Tsetse work provide lessons on other vectors? We think it can, but that's something which we'll have to go for the future. Okay, I'm going to close there just about. I just wanted one last thing. So I know that Francesco, you're a physicist, and you have heard very well of Tycho Brahe. And people who are physicists and mathematicians have heard of Tycho Brahe. A lot of scientists actually haven't heard of him. I just know that. But Tycho Brahe was a wealthy man who lived in Denmark. And his obsession was with the stars. And he was sufficiently wealthy that he had owned an island. Every biologist should have an island, and even an astronomer. There are no lights there. You could actually get really good measurements in the stars. He wasn't probably the world's greatest scientist, but what he did was he collected data. When he died, Kepler used those data to figure out, in particular, things like the fact that the orbit of Mars was an ellipse rather than a circle. He was completely dependent on Tycho Brahe, and Newton was basically, when he was basing his stuff on Kepler, and even Einstein, God bless him, basically was thinking very much about Newton. So it goes back in a lot of ways. It goes back to Tycho Brahe. And I will just leave you this quote from Finn Olsen, which you can read. But basically, it just stresses the importance in modern days of data. And so the last thing that I want to do, and I'm sorry, I've actually gone over it, is what we really need to do with these data is they have to be archived, not just archived so that you say, oh, well, I have to put these things out there, but archived to the point that future generations can use them. I'm sorry if I've gone a bit over time, but thank you very much for your attention.
Yeah, thank you very much for a fascinating talk. Thank you very much. The questions for our speaker. Any question? Please.
Thank you, John. I'm just wondering, like, this is a very almost like a closed and simple system. So what about the host and plant resources? The plant resources maybe already being kind of approximated by the NDVI, but what about the buffaloes, the cows, providing the plant resources to the flies?
That's right, and it's something we have been concerned about. What people at national parks have done over the years is they have done aerial surveys of the area in the whole of the minor pools, including around Rekomitjie, and essentially we can figure out that although there have been sort of problems as a consequence of these, when you get a vast drought and very, very high temperatures, you get die-off of animals. So you can have these short-term things, but basically there are still enough animals around Rekomitjie to support that. But it is a concern. Of course, we spend so much of our time actually working on the flies. It's very difficult to actually have time to try and estimate how many animals there are out there as well. But the indications, strong indications, are that there is sufficient. And of course, for a lot of the time, in fact, that we were there, we actually had our own herd of cattle of 30 or 40 cattle there the whole time. So that was actually supplementing the number of animals that were there in the wild as well. But it's a very good question.
Any further questions? Zura?
In which form is the data currently, and is it difficult to put it on the digital form if it's not already done?
Right. Large chunks of it are in digital form. So, for instance, I didn't say, but over that 11-year period, we actually we dissected more than 175,000 females, and I was solely. I mean, that was done by 5 different dissectors over most of that period of time, and I had somebody who actually punched the data in. But thereafter, I did the entire cleaning and built up the database and everything. So that is there in its totality. The only thing that's not there, so subsections of the data, as you saw, were dissected to find out whether they were infected or not. But there was a large subsection as well, where, having actually done the dissection, we popped everything back into a tube, sent it to the lab, find out how much fat was in there, how much blood was left. There are about 40,000 flies where those data are just in hard copy and they need to be digitized. An awful lot of the data from the early catches has not been digitized. That's still sitting on the walls in Rekomitjie, in the office. You can see the data are from Antelope Island. Most of that, the crude stuff, has all been digitized. I did actually start getting the individual marks on every single fly collected. That is still there in hard copy. So there's quite a lot of work still to be done on that thing. But there is a lot of work which is actually already out there, digitized, which is ready to be archived. But what needs to be done is somebody has to be sort of hired, essentially, to write very, very careful notes on exactly what's going on. Because even with, for instance, with the ovarian dissection, there are 30 or 40, for every fly, there are 30 or 40 variables which are being measured. So you need to say exactly what was actually done there. So that somebody down the line can actually pick it up and say, okay, I can see exactly what's being done here. This is how I can analyze it and show that these idiot Zimbabweans got it all wrong.
Any more questions? Then maybe we should ask our friends online if they have questions. Can I just peek into your laptop? If you see?
Sure.
There is a question here. No, just good afternoon. Okay, it doesn't seem
sorry,
that
Francesco,
we
there is
have
a
questions from our online. Let's see if anybody raised their hand. No. Oh, okay, doesn't seem to be the case. Then, John, thank you very much for the excellent talk. It was really fascinating, from counting flies to statistics. That's really incredible, and modeling. So thank you very much.